Let us develop a process of finding the inverse matrix of a non-singular matrix. So we start with the matrix A. If A is a non-singular matrix, then its inverse A to the negative 1 exists. Okay? And A times A inverse is equal to A inverse times A equal to the identity matrix I sub n, with A as an n by n matrix. So at this point, we will look for this inverse A inverse. Look for the inverse of A, or A to the negative 1. And let us denote this as x. Alright? So that means that A times x is equal to in, where A, x, and I are all matrices. Now we can rewrite the product AX equal to IN as A11, A12, up to A1N, A21, A22, up to A2N, down to the last row, AN1, AN2, up to ANN, multiplied by matrix X. And we know that the elements of matrix X are unknown. Let us denote the unknowns as X11, X12, and so on and so forth, X1N, X21, X22, up to X2N, down to XN1, XN2, up to XNN. And this product must equal the identity matrix 1, 0, dot, 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 0, 0, 1, dot, 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 0, down to the last row, 0, 0, and 1. Okay, so let us free up some space. There. Let us perform multiplication on these two matrices. So the first row, A multiplied to the first column. And this must equal the entry, the first row, first column of the matrix at the right, the identity matrix. So let us write down the equation A11 times X11 plus A12 times X21 plus, and so on and so forth, A1N times XN1 must equal 1. We go down to the second row of A and multiply it once again to the first column of matrix X. Second row, first column must equal 0. So X, or A to 1, A to 1, X11 plus A to 2, X to 1, until A to N, XN1 equal to 0. And we do that, the multiplication of every row of A to the first column of X, up to the last row, we will get AN1, last row of A multiplied to the first column, and that must equal 0. So AN1 times X11 plus AN2 X21 and so on and so forth plus ANN XN1 equal to 0. And what do we see here? We have just generated a system of n equations in n unknowns. And what are these unknowns? X11, X21, up to Xn1, which are actually the elements of the first column of the matrix X that we are looking for, right? And what we do to find the values X11 up to Xn1 is we apply Gauss-Jordan reduction method. So we shall write this as an augmented matrix first A, and then we append these elements, which are actually the first column of matrix I. Alright, and let us call that as, let's see, we use a different color. Let me call it as E sub 1. Okay, so we append E sub 1. A being the coefficient matrix. No? This is the coefficient matrix of the system. This is our system, and this is the coefficient matrix. And performing Gauss-Jordan reduction method, this will result to a reduced row echelon form, no? Assuming that this system is consistent. And if it is consistent, then we will be generating a unique solution. So this will transform into a matrix where the first n column is I, and then the last column will be B. And B is none other than the solution to the unknowns X11 up to Xn1. And let us call that as X sub 1. The entries along the first column of matrix X. Alright? So again, we work on this n system of n linear equations in n unknowns, where the unknowns are the entries of the first column of the inverse matrix, which we are denoting by X. That is the inverse matrix, A1. So, what we do next is we determine the values now of the second column of X. And to do that, we will repeat the process which we have already done previously. Okay. So multiply again every row of A to the second column of X, and it will result to the entries along the second column of the identity matrix. So A11 times X12 plus A12 X22 plus and so on and so forth plus A1n Xn2 equal to the first entry, which is 0. Then second row of A, A21 X12 plus A22 X22 plus and so on and so forth plus A sub 2n X sub n2 equal to 1. We do that again for all the rows of A until we reach the last row. AN1, X12 plus AN2, X22 plus and so on and so forth. ANN, XN2 equal to 0. So we have here another system of n equations in n unknowns. And what are these unknowns? X12, X22, X2n, which are actually the entries in the second column of the inverse matrix X that we are looking for. All right? And to solve for this system, we will once again apply Gauss-Jordan reduction method, where we have the coefficient matrix A appended by the second column of the identity matrix, which we are now calling as E2. Again, if this system of n equations is consistent, that means that there will be a unique solution. So the augmented matrix, after reduction to echelon form, we will be getting the first n column, which is the identity matrix, and the last column denoted by B sub 2. And this B sub 2 is none other than the solution or the values of x sub 2. And what is this x sub 2? This is actually the second column of the inverse matrix that we are looking for. Okay, so we repeat this for all columns of the inverse matrix or matrix X. And every time we perform this operation of multiplying every row of A to a column of X, we apply the Gauss-Jordan reduction method and come up with a solution or the values of the unknowns. Now, we see that repeated application will result to the same identity matrix for the first n columns of the resulting matrix in the reduced row echelon form. So we can do this simultaneously by appending to A columns E1, E2 up to En. And this will result to the identity matrix I together with the solution B, which is actually our matrix X, which is the inverse matrix of A. So in other words, this appended matrix can be written in the form A, and E1 up to En is none other than the identity matrix In. So we perform elementary row operations in order to transform this into reduced row echelon form in the form IB. Alright? So this will allow us to determine the elements of the inverse matrix. So let us summarize this. So the first step is to, of course, we are given matrix A. So first step is to form the n by 2n augmented matrix AI. Alright, and the second step is to reduce the above matrix to echelon form. Let us call this as the augmented matrix CD. Alright. Third, if C, the n by n matrix is equal to the identity matrix In, then that means that the inverse matrix A to the negative 1 is equal to the last n columns of the resulting matrix. On the other hand, if C is not equal to the identity matrix In, then A is a singular matrix. Meaning to say, A has no inverse. Alright? So these are the three simple steps on how to find the inverse of a matrix if it exists. So let us have an example. Given matrix A, 1, 2, negative 1, 3, negative 1, 2, 1, negative 2, and 1. So let us find the inverse A to the negative 1 if it exists. Alright? So the first step is to form the augmented matrix AIN. Since A is a 3 by 3 matrix, then I is of order 3. Right? So that becomes 1, 2, negative 1, 3, negative 1, 2, 1, negative 2, 1. And then we augment this by the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Alright? And we will reduce this to reduced row echelon form. And we are familiar with the process now. So 1, 2, negative 1, 1, 0, 0, 3, negative 1, 2, 0, 1, 0, 1, negative 2, 1, 0, 0, 1. Since the first element of the first row is already a 1, we simply rewrite the first row. 1, 2, negative 1, 1, 0, 0. And then we need to multiply this row, the first row, by negative 3. Negative 3 times row 1 plus row 2 to make the entry below that leading entry into A0. So, negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times 2 is negative 6, and negative 1 is negative 7. Negative 3 times negative 1 is positive 3, plus 2 is 5. Negative 3 times 1 is negative 3, and 0 is negative 3. Negative 3 times 0 is 0, plus 1 is 1. Negative 3 times 0 is 0, plus 0 is 0. Okay? Next, we need to make this a 0. So we multiply row 1 by negative 1. So negative row 1 plus row 3. Okay, so negative 1 plus 1, that will be 0. Negative 2 and negative 2 is negative 4. Negative 1 times negative 1 is positive 1, and 1 is 2. Negative 1 and 0 is negative 1. 0 and 0 is 0. 0 and 1 is 1. Okay? Next, we consider the first non-zero entry at the second row, which is negative 7. So what do we do with this? We multiply this by negative 1 over 7. Okay? And what do we get? 0, 1, negative 5 over 7, 3 over 7, negative 1 over 7, and 0. Okay? So 1, 2, negative 1, 1, 0, 0, 0, negative 4, 2, negative 1, 0, and 1. Okay? So this is now a leading entry. So we rewrite the second row. 0, 1, negative 5 over 7, 3 over 7, negative 1 over 7, and 0. And we shall multiply this by negative 2. Negative 2 to row 2 plus row 1. So negative 2 times 0 is 0 plus 1 is 1. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times negative 5 over 7 minus 1 will give us 3 over 7. Negative 2 times 3 over 7 is negative 6 over 7 plus 1 will give us 1 over 7. Negative 2 times negative 1 over 7 is positive 2 over 7 plus 0 is 2 over 7. Negative 2 times 0 is 0 plus 0 is still 0. Okay? Then we have to make this a 0. So we multiply the second row by 4 and add it to row 3. Okay, so 4 times 0 is 0 plus 0 is 0. 4 times 1 is 4 minus 4 is 0. 4 times negative 5 over 7 plus 2 will give us negative 6 over 7. Then 4 times 3 over 7 is 12 over 7 plus negative 1 is 5 over 7. 4 times negative 1 over 7 is negative 4 over 7 minus 1 is negative 4 over 7. And 4 times 0 is 0 plus 1 is 1. Okay. So, we consider the first non-zero entry of the third row, negative 6 over 7. So what do we do here? We multiply row 3 by negative 7 over 6. Okay? To make it into a 1. So 0, 0, negative 6 over 7 times negative 7 over 6 is of course 1. And then 5 over 7 times negative 7 over 6 is negative 5 over 6. Negative 4 over 7 times negative 7 over 6 is positive 4 over 6, or 2/3. So let us leave it as it is, 4 over 6. Then later on, we'll just reduce it to lowest terms. And then 1 times negative 7 over 6 is negative 7 over 6. Okay, so this is a leading entry, and entries above must become 0. So 3 over 7 needs to become 0. So we multiply the third row by negative 3 over 7 and add it to row 1. So negative 3 over 7 times 0 is 0 plus 1 is 1. Negative 3 over 7 times 0 is 0 plus 0 is 0. Negative 3 over 7 times 1 is negative 3 over 7 plus 3 over 7 is of course 0. Negative 3 over 7 times negative 5 over 6 plus 1 over 7. So that will be 15 over. Negative 3 over 7 times negative 5 over 6 is 15 over 42. And then plus 1 over 7. 1 over 7 is 6 over 42. Okay, so 21 over 42. And that is by 7, 3 over 6. Okay, so 3 over 6. So next, negative 3 over 7 times 4 over 6. Negative 3 over 7 times 4 over 6. That gives us negative 12 over 42. And then add to it 2 over 7. 2 over 7 is 12 over 42. So that becomes 0. Next, negative 3 over 7 times negative 7 over 6 is 21 over 42 plus 0 is 21 over 42 by 7 is 3 over 6, or 1/2. Then we go to the second row. We need to transform negative 5 over 7 into a 0. So we shall multiply the third row by positive 5 over 7 and add it to row 2. So 5 over 7 times 0 is 0, plus 0 is 0. 5 over 7 times 0 is 0, plus 1 is 1. 5 over 7 times 1 is 5 over 7, minus 5 over 7 is 0. 5 over 7 times negative 5 over 6 is negative 25 over 42. And add it to 3 over 7. 3 over 7 is 18 over 42. So that gives us negative 7 over 42, or negative 1 over 6. Negative 1 over 6. Next, 5 over 7 times 4 over 6 gives us 20 over 42, plus or minus 1 over 7, that is 6 over 42. 20 minus 6 is 14 over 42, or 2 over 6. 2 over 6. Then 5 over 7 times negative 7 over 6 gives me negative 35 over 42, and then add it to 0 is 35 over 42, or negative 5 over 6. Negative 5 over 6. Okay? So, what do we see here? We have already transformed this into reduced row echelon form. And we see that the first n columns is actually the identity matrix In, or I sub 3. So that means that this is our matrix D, or the inverse of A. So 3 over 6, 0, 3 over 6, negative 1 over 6, 2 over 6, negative 5 over 6, negative 5 over 6, 4 over 6, negative 7 over 6. But we have to check this now. So we check by rewriting matrix A, 1, 2, negative 1, 3, negative 1, 2, 1, negative 2, 1, multiplied to 3 over 6, 0, 3 over 6, negative 1 over 6, 2 over 6, negative 5 over 6, negative 5 over 6, 4 over 6, negative 7 over 6. Okay? So, first row, first column. 1/2. 1 times 3 over 6 is 3 over 6. 2 times negative 1 over 6 is negative 2 over 6. Negative 1 times negative 5 over 6 is positive 5 over 6. 5 and 3 is 8, minus 2 is 6 over 6, or 1. Okay? So that is equal to 1. Next. First row multiplied to the second column. 1 times 0 is 0. 2 times 2 over 6 is 4 over 6. Negative 1 times 4 over 6 is negative 4 over 6. And that is equal to 0. So that is equal to 0. Then, 1 to negative 1 multiplied to 3 over 6, negative 5 over 6, negative 7 over 6. So 1 times 3 over 6 is 3 over 6. 2 times negative 5 over 6 is negative 10 over 6. Negative 1 times negative 7 is positive 7 over 6. 3, negative 10, and 7, that will be 0 over 6 or 0. So this is equal to 0. We go down to the second row, multiplied first to the first column, we get 3 times 3 over 6 is 9 over 6. Negative 1 times negative 1 over 6 is positive 1 over 6. 2 times negative 5 is negative 10 over 6. 9, 1, and negative 10 is 0. Okay? So we have 0. Next, second row, second column. 3 times 0 is 0. Negative 1 times 2 over 6 is negative 2 over 6. 2 times 4 over 6 is 8 over 6. Negative 2 plus 8 is 6 over 6 or 1. Next, second row, third column. 3 times 3 over 6 is 9 over 6. Negative 1 times negative 5 over 6 is positive 5 over 6. 2 times negative 7 is negative 14 over 6. 9, 5, and negative 14 is 0. Okay, so third row. Third row to the first column. 1 times 3 over 6 is 3 over 6. Negative 2 times negative 1 over 6 is negative positive 2 over 6. 1 times negative 5 over 6 is negative 5 over 6. 3 to negative 5 is 0. Then, third row to second column. 1 times 0 is 0. Negative 2 times 2 over 6 is negative 4 over 6. 1 times 4 over 6 is 4 over 6. 4 over 6 minus 4 over 6 is 0. And finally, third row, third column. 1 times 3 over 6 is 3 over 6. Negative 2 times negative 5 over 6 is 10 over 6. 1 times negative 7 over 6 is negative 7 over 6. 3 and 10 is 13 minus 7 is 6 over 6 or 1. Okay, and so we see that this is our I3. So therefore, indeed, our A inverse is 3 over 6 or 1 half, 0, 1 half, negative 1 over 6, 1 third, negative 5 over 6, negative 5 over 6, 2 thirds, and negative 7 over 6. Okay?